So okay, now we are ready to start the fourth lecture on the acoustical transducers. This will be about the MEMS condenser microphones. And today I hope to teach you how to present the model and how to work with this model of a microphone. Oops. So as you know, we are with a condenser microphone in the reversible effects. So the models would hold for something like parallel plate transducers, maybe not so much different from piezoelectric devices, externally biased, but in this situation, or electret could also be, is not very different of FET microphones. So the message is we have a parallel plate system, and we want to try to understand how to model this. And what we had in the last lecture that was sensitivity. Just to remind, the system sensitivity open loop is the combination of electrical sensitivity given in the bias on the condenser divided by the distance of the two plates, very easy, electrostatic field strength, and multiplied by the mechanical sensitivity, which is basically given by the compliance of the diaphragm or the inverse of the spring constant of this system. And this gives our total sensitivity. And this we will model over the frequency in this lecture. Yeah, and from the electrical readout circuitry is a takeaway that to measure gap distance changing variable gap capacitor, we should use a constant charge biasing that results in a constant force over the two plates, which is not dependent on the displacement of the diaphragm. And this is an advantage because then we have a better chance for linear transducers. So the external bias on the other hand side is limited by the so-called pull-in voltage. So if we have a voltage on our system and it is going higher than this pull-in voltage, then the system could collapse. The force of the electrostatic field is then stronger than the restoring spring force of the diaphragm. And when we see there's the compliance of the diaphragm in again, or the spring constant, and the gap is of course very sensitive for this reason. Finally, we learned that when you achieve the pull-in voltage, you have consumed somehow 1/3 of the gap in terms of displacement of your diaphragm. And then we're showing different cases on how to generate those compliances of membranes. There's at least 3 ways of doing it: the diaphragm in membrane shape, a plate on the other hand side, which is bending stiff, or even a floating plate, which has a different kind of a bending idea. And this is subject to fabrication and design. However, to bring such kind of diaphragms, MEMS engineers have been very creative in bringing endless ways of diaphragm transducers. So now we go a little bit into the key performance parameters that are responsible to characterize a high quality microphone. So it is in total basically 3 parameters that are governing here. The first and maybe most decisive one is the signal to noise ratio. So as every sensor, you want to display very tiny signals. So you have a noise limitation maybe, which is given by the internal losses of your microphone or of your sensor. That is basically the limitation of smallest signals. And the lower this limit is, of course, the further or the more remote you can take recordings. Or in the case of speech recognition, understanding depends also on the noise level. the lower the noise level is, the better the microphone can take tiny signals or specific items in speech. And on the other hand side, it is of course the signal, the maximum signal that you can transfer. So this gives the signal to noise ratio. It is quite important parameter. And as I said, the maximum sound pressure level is typically also characterized with a certain distortion. The higher the signals are, then you might have issues, for example, wind pop noise. You know this if you do a recording with your smartphone, you have wind around. The wind is acting on the sound port, is giving this kind of a pop noise. This guy here in the convertible has certainly issues with this. And also sometimes a situation like this YouTube video, where is in fact a recording with a very, very good microphone that you can go to the monitors or to the musicians and you have a recording without clipping, so not even the maximum sound pressure level is achieved. So there's a good chance you need to bring this. Basically, this again goes into the dynamic range of your system. And you want to have low distortion at high sound pressure level. That means the transfer of signals should be clean and clear and a nice audio experience. And all this is under the constraints of size. It's just a staple of iPhones until I guess this iPhone 7. The others don't get thinner anymore, but in other ways complex. Somehow these microphones have to fit in here. And this is a height and the size limitations. Basically, from generation to generation, it was requested to bring the same performance or better performance in a smaller form factor. And this is, of course, physically an issue. There was even ideas to get flexible phones, and this is coming back again, maybe. So then your device should be so small or even bendable. And this is the engineering request, bring all this together. How does this look in numbers or in scales? As you remember, we have our sound pressure level defined in decibel, and the 0 dB is the human ear equivalent sound pressure level of 20 micropascal. And if you have a typical microphone, we characterize this with the sensitivity, which is defined as the sound pressure level recorded, or the signal for a sound pressure level equal to 1 Pascal. 1 Pascal makes it 94 dB sound pressure level. So this is your sensitivity definition. And then from the self noise of your microphone, we go to the equivalent noise level. So the voltage that is coming out of the terminals of your microphone is expressed in a equivalent sound pressure level that would give exactly this output signal. And for a quite good microphone, this may be 25 dB sound pressure level. It is really, really tiny and little signal. You wouldn't hear, it's like a very quiet room. And okay, we give also a total harmonic distortion at the 1 Pascal, which is giving a number for linearity of your device. It should be small, of course, at 94 dB SPL. And somewhere we reach a limit of sound pressure levels where the total harmonic distortion gets high. Typically, it is rated for 10% total harmonic distortion. And at this level, we define the acoustic overload point. So this is then the maximum sound pressure level that the microphone might transfer without too high distortion. We will see later what it means. So then in the level diagram, we define the signal noise ratio from the eigennoise level to the sensitivity, of course, and the dynamic range is from the eigennoise level up to the acoustic overload point. And this is data sheet levels, simply to say what is happening. We have maybe a situation in the phone where we have from 0 to the bias voltage a certain range, say it is 3.8 volts. Then from the electronics, we have a threshold limit of the electronics, depending on the transistors which is used. I say maybe 300 millivolts. And then the range that we can use is maximum this around about 3.5 volts. So in this range, if you have a very good transistor, you can then transfer audio signals. Here's a sine wave. So this blue one is of course unaffected, but if you have very high signals, then even you cannot transfer the whole sine, and it is clipping if it is reaching the bias supply or the rails, how we say, or the VCC. Then this is simply cut off, and this gives overtones simply from this is then the total harmonic distortion that we would feel strong, and it is sounding very bad. Just to see what this means, if I have a bias of 3.8 volts, finally I can have an amplitude of 1.75 volts min max each side, yeah, and an RMS voltage of 1.24 volts only. And with this, I want to achieve a sensitivity of minus 38 dB volts per Pascal. This is something like 12 millivolts per Pascal. And of course, I measure some noise voltage, say 4 to 5 microvolts. So here's the sensitivity in millivolts per Pascal. This is at 1 Pascal. And that means we get a clipping from this maximum RMS of with 4.9 Pascal. This, of course, with respect to the RMS value, which is a 108 dB sound pressure level max. This is not a very good microphone. It has not a lot of headroom, but this is typically the case. And still, if I look from sensitivity to the eigennoise level, I have the 69 dB signal noise ratio, and of course, the 83 or something up to the clipping point. And this is somehow the level plan which you can run up and down, whatever requirements you have. You have to adjust sensitivity or work on the noise level, or maybe even you do something to get your device more linear. And last but not least, maybe you have to get higher bias supply. But since we are always driven to use single cell or dual cell phones, there's a little chance on reducing or increasing this very much. Okay, this is how microphones are described. And I give you a little insight into what is going on in terms of dynamic range. I have here my sound pressure levels from 0 to 220 dB SPL, which is 20 micropascal to 20 bars. Sure, this is something beyond microphone. And I want to express this in terms of center displacement of a 1 millimeter diaphragm. So if you are in the linear range of the transducer, we see that some picometers is the displacement of a diaphragm. This is the noise equivalent displacement roundabout. Then at some silent or normal torque, we have still only sub-nanometer displacement of my diaphragm. So it's still not a lot. Even if you look at the sensitivity point 1 Pascal, around about 10 nanometers displacement, this is the normal displacement. If you have very high sound pressure level, which are close to the limitation, 120 dB SPL is around, what is this? 0.1, 0.2 micrometers, some 200 nanometers. Just for reference, the thickness of the diaphragm is around about 300 nanometers. So even in this extreme case, we are not moving the diaphragm more than its typical thickness. So it's always a small displacement. The air gap is some 2 micrometer. And of course, you can move the diaphragm further. Then it's highly nonlinear. And this happening like by pop noise, wind noise, which is extreme. So 140 decibels you can have easily at low frequencies like a door slam or clapping with your hands. This is always not very, it doesn't harm your hearing because it's low frequencies. If you have the same sound pressure level at 1 kilohertz, you get severe issues, of course. And then 2 micrometer displacement is also a critical point, or this is the point where the diaphragm is hitting the membrane. And we were talking about this pull in here again, this picture where we drive up the supply voltage on this transducer and see how the diaphragm is hitting the back plate. This especially can be a measure for the sensitivity of the device or mechanical sensitivity. Yeah, and beyond this, of course, from a lot of studies on a very special microphone, you find a fracture limit where the diaphragm is blown off at several bars or tens of bars for very short times, like milliseconds they can hold, but of course is close to the situation of burst of the membrane. Then the device will fail. So of course this failure we will discuss later on in discussion on fabrication, packaging and testing and so on. We want to make this range, the blue range, the linear range, available to a microphone. And of course, it should always withstand all these nasty situations beyond and don't do harm to the device or get very bad acoustical events. Just to give again a bit the scaling, I put in here the diameter is 1 millimeter, thickness of the diaphragm, which is the whole microphone from top side. You see the perforated plate from above. And if you cut in here a side, you see then here we have part of this perforated plate, the tiny membrane below, which is 300 nanometers, and the air gap is here 2 micrometer, and then the electrode on top is something also like 2 micrometer. And then, as I said, displacement in noise situation is some picometers. And I try to scale this always. If I say the diaphragm is as thick as paper, a little thicker than typical paper, then I would have a membrane of 1 meter in diameter, an air gap of 2 millimeters, so you can see this somehow, but still my displacement resolution is 10 nanometers. And just to feel what it means to seeing this resolution of noise of a vibrating membrane, I say a 1 millimeter displacement from noise we could easily see, but then our diaphragm is some 100 kilometers in diameter and the air gap is some 200 meters high. This is a diameter in the range from Freiburg to Bodensee, and I have here close by the Thyssen Tower for elevator testing is 240 meters high. This would fit into the air gap somehow. So this is just the relations to understand what job we have to do. And we have to, of course, control this and not only design it. So getting a flat diaphragm for this air gap and stuff like this is finally the challenge. Okay, now we're talking about fluidic resistances. Why do we do so? If we look again at the construction elements of those microphones, I always say it is a design of holes rather than of silicon. Yeah. Well, if you look from outside, we have a sound port. This will play an important role. Even the hole before the sound port, so whatever the housing of your telephone is doing is an important design parameter, but not in the control of the microphone designer. So his duty starts with a sound port. Then he has his chip with this back cavity is also a hole which has acoustic performance. Our whole perforated backplate is clear that the sound has to move through this plate. It should be transparent, so these holes have to be under control. And last but not least, this ventilation hole, these tiny holes that allow to ventilate air in the microphone for static pressure relief. They are important as well. So these are basically fluidic channels that we design. And if we want to design those specifically, we have to get fluidic solutions for velocity in different direction, pressure, density of air, and of course is depending on the temperature. This we want to understand in general, and we start very top level with those 6 fundamental equations that we have seen partially before. So we have the ideal, the state of ideal gases, P, pressure times volume is equal or constant, and depends only on the temperature and gas constants. We have, of course, the mass conservation, where we see that changes of mass can be balanced by a flow-through volume, or but needs to be conserved. So whenever we have a change of density over time, or a change of mass flow through a volume, this has to equal each other. So it cannot be generated any gas at any point, but it is simply balanced. Now, of course, we have energy conservation. We come to this on the next slide, and the 3 Newtonian equations for motion, they make up the so-called Navier-Stokes equation, which is a very generalized equation to describe flow. In different situations, you need different of those equations. I simply sketch it here. Especially the energy conservation in fluidic systems is, of course, quite a complex situation, going down to the molecular physics. For example, here, the change of the inner energy over time. Inner energy, what is this? You have molecules in the gas, maybe monoatomar or multi-atomar molecules. They have, from their boundary, specific inner energy, vibration or rotation, and this will be used in infrared absorption spectroscopy, for example. And why is this now a fluidic term? Imagine, maybe you have heard about so-called photoacoustic sensing. If we irradiate with specific wavelengths into a gas, where we hit exactly such a resonant or such a vibration energy, we excite it, and then we excite our gas, it is excited and has a higher state, and then we switch off the radiation, it is falling back, is relaxing again. We can do this with an audio frequency, say 100 Hertz. We pump it up and up, and then you can hear the gas due to this pressure event. So this is basically the effect used in photoacoustic gas sensors. So here we come to the inner energy, but it's not really relevant for the microphones. Then, of course, we have the work of expansion or compression whenever we squeeze or expand a volume. Also not a situation that we will do to microphones in higher excitations. And this is balanced, of course, by heat exchange, by conduction with the Boltzmann constant. So whenever you have temperature gradients, then this will cause also an effect, an energy effect. And then inner friction is also something. We have, of course, gas molecules hitting each other. This is kind of heat dissipation. And of course, there is a coefficient of friction with this. Yeah, heat exchange and dissipation we very often neglect if we have, so to say, adiabatic exchanges, or we do fluctuation that are on higher frequencies, so that heat exchange cannot happen. Of course, there is situation at low frequencies where we have to accept those effects as well. But for the moment, we can exclude it. So this we learned from the energy conservation. Yes, and then comes this description out of the Newtonian equations, the Navier-Stokes equation. So a very complex equation, doesn't look so much, but if people are trying to solve this, they get into deep situations. We try to explain what it is. Yeah, I say it's difficult, or nobody has solved it so far. If you look at the Clemens list of millennium problems, I guess I have it open somewhere. Yeah, here. This is an institute which is granting millennium problems like the Navier-Stokes equation or the Riemann hypothesis. So the one who is solving it after their request will get a $1 million fee. But this, I guess they don't have the money reserved because nobody can solve it, but would be a challenge by itself. Now look into this Navier-Stokes equation. We have on the left-hand side inertial effects. So dV over dt is simply if we had a tube system and we change the pressure difference, or we change the velocity over time in a tubed system, yeah, or in any kind of a fluidic system. So this is an inertial effect. This is important. It can also be that it is changing a kind of a compression. So we have a change of velocity over space, while we have this funnel, for example. At the entrance, we have a special profile. Afterwards, we have a higher profile. This is also a kind of acceleration of our fluidic system, is an inertial effect. Of course, there's an external force who's driving this, an external force simply. Then we have a gradient of pressure due to an external pressure gradient, for example, which could be static. We have friction losses. We see a secondary rate over velocity. That can happen. And then we have a force due to the change of volume. So this is, again, a situation which is highly nonlinear. So if we could solve this, we could answer all the questions, but we know already this is not been done so far, so we will not try to do here. For this reason, simply people help themselves for a long time with simplifications. And to judge on simplifications from the engineering of the last 100 years or so, there have been developed characteristic numbers which engineers typically use to compare their challenge in terms of characteristic features. For example, if we start with the Reynolds number, this is characterizing a specific length, can be a characteristic length like the length of a boat or anything else, its velocity, and with respect to the viscosity that it is floating in. And this in air is different than in liquids, of course. And whenever this Reynolds number is much smaller than 1, then we don't have these accelerated situations. We can neglect inertia. So this can help simplifying. We have the Mach number. Everybody knows the Mach number, which is comparing the actual velocity with the speed of sound. So if you have small velocities, then we can neglect compression. Compression, which everybody knows, is the origin of this hypersonic bangs that we hear if an airplane is compressing air in front of its nose while flying with or beyond velocity of sound. Yeah. And the Stokes number finally is a dynamic measure and it somehow relates the frequency which a fluid is oscillating with, also again with the viscosity. And okay, if the frequency is low or the Stokes number is small, then the fluid can follow this oscillation. Yeah, and now the Stokes equation, for example, if Reynolds and Stokes number is small, that means we can neglect the moments of inertia. Then we can neglect, of course, these terms. We can further simplify. If we have no compression, that means we have in the continuity equation the term zero change of density over time. This simplifies further. And last but not least, we get the incompressible Stokes equation. When we say we don't compress anything, then we can simplify further. And this is the ways to find out the equation that can finally be linearized or solved for special problems. And we pick some problems out here. So these are simplified equations finally. The special cases are with respect to the situation in a microphone or in the speaker or whatever acoustic device we have. And one very straight example is flow through a channel, a lateral flow through between two plates of a certain area and a given height. Everybody knows that we have a drag force at the surfaces, and but typically a profile of flow in between those plates. And this can be the outflow between two diaphragms, for example. Yeah, we simplify to get the two-dimensional Hagen-Poiseuille flux. We have a stationary condition, sorry. So the stationary condition is if you have a constant gradient along this channel. We have an incompressible fluid, which is in small displacements the case. And of course, the gradient of pressure is linear, which is also in the CD state easy to say. And then we check velocity in one direction. And we say also that the side condition, we have no drag flow at the wall sides. So there's zero at the both ends. There's, however, also a flow where you generate a slip at the wall, a so-called slip flow. Then this condition would not hold, and we will see such situations later. They are realistic, but this is the very simplest one. And we again simplify our Navier-Stokes equation. It's now very simple. Second derivative in one dimension, second derivative of the velocity over the cross section is then constant. Yeah, simply this pressure gradient divided by the viscosity. And this we can integrate 2 times, and then we get this squared profile across the cross section. And if we solve this over the width of the channel for such a flux, so the width is wide, then we get the flux integrated over the height, which is this special formula. And we see the height is with the third order in here. So the higher the system, the higher the flux can be. And of course, now we have a relation between the pressure drop across this channel and the flux, which is exactly then the resistance of this system. And we get then the slit resistance or acoustical slit resistance as proportional to the length of the slit. Of course, the longer the slit is, the higher the resistance, but inverse proportional to the width of it and the height to the third. So this tells us already if we have tiny channels, we will get into trouble, because then these fluidic resistance get high, and they are important to define bandwidth and noise of a microphone. So the second situation is very simple. It's quite the same as before, but most often we don't have slits, but tubes. So there's a tube with a length L and the radius R. We do the same in cylindric coordinate, can solve again. And now we get a tube resistance, which is proportional again to the length, but inverse proportional to the radius to the fourth. So before we had the height to the third, now the radius to the fourth. Of course, we have a more dense system and a more sensitive parameter with radius compared to the height. And you see already that tubes or holes, finally a hole is also a short tube, then the radius is very, very sensitive to its resistance. Yeah, one special case is a very, very short channel, which we call an aperture. So virtually there's no length of this hole compared to its radius, let's say a few hundred nanometers thickness and several micrometer in diameter, then we can simplify it this way, and we get an aperture resistance which we have with the radius to the third in terms of resistance. Of course, then the thickness is 1 order less, and this is simply an FEM simulation to control this simple expression. It holds quite well. Yes, a typical velocity profile through a tiny hole. Then we use the so-called Reynolds equation if we want to solve the situation that the flow is not generated by a pressure gradient across a plate, but by, so to say, squeezing the plate up and down on this air cushion. So if you have a parallel plate displacement, of course, the air has to go in and out of this situation. And this is described with this Reynolds equation. So we have somehow a plate A times B and a movement out of this effect. You can imagine if you had very, very large plates, this would cause like a spring effect, because you have the air cushion by compression expansion, and you have, due to the in and out flow, also a damping effect. So we know all this is the principle of in car how dampers, car dampers, the squeeze and damping combination. So of course, in our MEMS situations, we want to avoid those effects, but we have to understand what it is. So now we simplify again the Navier-Stokes equation. But we cannot be so simple as before, and therefore we have the partial equation that is given here, and we have to limit to very small displacement out of the height and respectively smaller pressure changes with respect to the total pressure. So as we said before, our microphone is moving some nanometers with respect to some micrometer. So this holds, and the pressure change, or the delta pressure 1 Pascal against, let's say, 1000 Pascal, which is normal pressure. No, 10,000 Pascal is normal pressure. This is true. So we can then use this linearized Reynolds equation, and even this is being solved, and I give you the literature for it, but don't run with you through this solution. The solution finally for the force which is generated by doing so is a normed compression part, which is a real part, and a normed fluidic loss, which is an imaginary solution. So we divide it simply by a constant, which is driven with the displacement and a compression and a fluidic loss term. And the solution for those friction and spring terms is given here as a series with relation to the ratio of width times A times B. And we simplify this sigma here, which is called the squeeze number, like a characteristic number for the effects that are showing up here. Squeeze number, simply if it is high, we can imagine then squeezing is predominant. If it is low, it is losses is high. Yeah, spring versus friction. And this squeeze number, we have the characteristic lengths, maybe A or B, which one is smaller, is then relevant. And we see, of course, there's again the height of the gap in with squared. There's also omega, the frequency which you use to generate squeeze. Of course, the higher the frequency you activate such a system, the stronger the squeeze effect is, the stronger the friction will be. And it is clear that if you have very high frequency, such a system gets more or less stiff. if you do it very slow, then the air can escape, and you have, of course, the friction effect, but the spring is then little. So this is somehow the phenomenology of squeeze numbers and squeezing. And there's, of course, for this situation also some models or some solutions over the squeeze number. So if squeeze number is a parameter, we can see the spring force and the friction forces, how they develop. As said, the higher the squeeze number, the stronger the spring effect is, and the friction is initially predominant, but later is getting lower in relation to the spring force. Now, just to get an idea of what this means, where is our typical squeeze numbers? I take a 2 micrometer high system. I don't know which characteristic, the characteristic length is here. And I check what is the squeeze number. So if I have 0.5 millimeter characteristic length, this would be the size of a microphone, I would get a squeeze number 80, so very high in this case, and that would be like a parallel plate system without any holes in one of those plates. I would get a strong spring force, and maybe my system wouldn't get any signal anymore. And for this reason, you see already that we need to perforate one of the plates. 100 micrometer, the squeeze number is already 3. We are here in 3. Whatever ratio of dimension you have, the spring effect is nearly gone. And realistic characteristic numbers, hole to hole or something, is in the range of 10 micrometer. Then our squeeze number is so small that the spring effect is nearly negligible, but of course a friction loss can still be the case, because then the move is squeezed in and out. So this gives us already an indication how the loss of force situations are related in those systems. Of course, people have studied this up and down. For example, Mr. Skor in 1967. So it's a very, very old paper, but always cited if people start designing microphones, because he has solved the fluidic resistance analytically, of course, and those guys were always very creative in all these analytic solutions for a situation where you have holes in a grid aligned, so a square grid, for example, and a moving diaphragm, and the moving diaphragm is squeezing out the air and in the air through a perforated device. And then, of course, he is relating the range where the air is pushing in and out of such a hole with the distance of the holes and the diameter of the holes. And of course, if you try to optimize your system, you very much identify that you should do a hexagonal situation, because then the furthest point to a hole is in average smaller than in the square situations, like the densest packaging of bolts. So this is describing quite well. Nowadays, people like very much FEM simulations and rather run an ANSYS than such an analytic. It's a more modern situation where we see the pressure drop along the holes. Is a unit cell, hexagonal. He could have done also a trigonal unit cell, I would say, and spare some computational time. Of course, between 3 holes in the center, the furthest apart, we have the higher loss from there. And if you compare to the square situation, the situation is a little less. And then we find descriptions for friction and spring losses out of this. Still, if you see here the numbers, Z by H, that is the pitch of the holes and height of the gap. So if we have a that equal 20, so we have 20 or 40 micrometer distance between holes for a 2 micron gap. And in such a situation, again, we see squeeze numbers are low, squeeze effect is negligible, but friction losses are still relevant. So typical situations in here. Yes, okay. everything so far was reflecting linear situations, or we are in the range of continuity. Of course, we have to check always for the molecular characteristic of our media of gas, of air. Yeah? And we had already those characteristic numbers. I put here another number, it's the Knudsen number, which is reflecting the free mean path of molecules in media with the characteristic lengths in your systems. And from statistics, we know that this free mean path is around about 60 nanometers at normal pressure. And this is the situation of a whenever you are in the range of these typical free mean lengths or paths of molecules, and you have sub 60 nanometer systems, it's statistically possible that you don't find a molecule inside this gap just by statistical means, or we are in the range of molecular movements. So we have to see where we are working. So we have continuity, continuum flow for dimensions around 100 micrometer typically. Everything is valid, and all what we reflected before is also valid. Already in the range between 10 and 1 micrometer, we get this what I call the slip flow regime. So you might eventually have not a zero flow at the side wall, and you have to do computational effort to identify this slip along a wall. Of course, then there's a transition regime, but for sure, in the Knudsen number 10, which is 6 nanometer, really nanomechanics, then we are talking about free molecule flow. And this is nothing we can discuss with the equations before. Then we have to do maybe Monte Carlo simulations or molecular dynamics. So, but nevertheless, microphone is more on the left-hand side, and the equations before, they hold quite well. And we have dimension typically like the thickness in nanometers, so that flows are still realistically to be considered continuous. Now, for this reason, we be able to do lumped element modeling. Yeah. Once again, how is this microphone looking like? We saw these pictures already. I have always this graph here with a diaphragm, air gap, and a top back plate. Here we have cut through the membrane system, a little higher resolution than here. We see here the diaphragm, 300 nanometers, silicon or polysilicon. We have an air gap. In this picture, it is still filled with a sacrificial layer, which is removed finally and giving access for the air. And we see here one perforation hole, part of another perforation hole. So in between, the air has to move in and out. And we see already this in the range 2 to 1 or 4 to 1 something. And the backplate is of course stiff because thick, and it should not bend under acoustic or electrostatic load. So it's around about 5 times thicker than the membrane. And what we discuss in the fabrication is those needle type of structures which are inside the backplate. They simply prevent the membrane from sticking if it comes in contact with the backplate. So they reduce the contact force effectively. So this is basically the construction. And of course, this microphone needs to come into a housing. And I sketch it very simple here. We have again our substrate with the edged cavity inside. Is just a cut through with the diaphragm with a hole inside, so that this enclosed back volume can equalize with the environment, at least at low frequencies. Imagine you heat up your system, then it would glow. If it is not vented, we have a gap, and between the backplate and the membrane, there's a little oxide clamping it, so you don't get into electrical contact. We have all the perforation holes inside here, very schematically sketched. Then we call this the front volume because the black is the housing, behind it is sealing, and in front it's giving rise to a sound port. So air or sound comes in here, goes through the backplate, moves the diaphragm, and hits the back volume, so to say. Yeah, and of course, since we have the housing, no sound comes from the rear side. Now we have to use our lumped element model to sketch the model. I remind again from maybe the second lecture that we will use now the first analogy of force voltage analogy. So this is impedance true, and we will use inductors to describe masses, resistances to describe loss terms, capacitance to describe compliances or inverse springs, and then we can add up those voltage conform or force conform as in the mechanical model. So if you apply this in here, we go very straight. We have outside a sound source, which is a pressure generator here in our electrical equivalent, generating a flux. This somehow enters into the microphone area. This is a so-called radiation impedance. How it is describing from the free field to the port, the impedance transformation. Then the port itself is a hole, so we define also an impedance for that. Then I simplify and define a MEMS impedance. So whatever is here, perforation and the gap and the diaphragm. And I define an impedance for the back plate. And we have a bypass impedance for the ventilation. So this is strictly how the forces are adding up if we drive from outside into our system. And now, of course, we have to detail the impedances. Of course, each impedance could consist of a mass, a spring, and maybe a loss term. But we step by step, we go through this and see what is relevant or maybe less relevant. If we start with the radiation impedance, I know that there is no compliance, there's no spring effect or very negligible. So we have a radiation mass, is somehow the mass of air which is actuated in radiating sound into this. And we did this in one of the former lectures. There's this generalized description of the real and imaginary part of the radiation impedance for certain situations. And of course, there's the radiation resistance, so losses due to radiation. What you see also, we put here a fixed term and not a frequency-dependent term. While this is frequency-dependent with wavelengths scaling, we can do this for a critical number. Later on, we will see even that both of the terms are most often not relevant. So next, we come to the port situation. So the port impedance is, again, we say there's in this spout, in this hole, there's a mass which is resonating with the front volume. Yeah, you remember the Helmholtz resonator. So it's like a funnel and a volume, and this gets in resonance to each other. So this front volume is quite large and acts like a spring, basically. And you see we have an acoustical compliance for this front volume, which is going to ground. All compliances, acoustical compliance, need to go to ground. Then we have the mass inside this hole, and of course we have to give it also a resistance. Since this is a smaller hole, we will have some loss term from there. And then we have described already the sound part. Next, we do the simple one, is the ventilation, where maybe we have only a small, tiny hole in our diaphragm. And this tiny hole will have nearly no mass effect, and spring effect we can neglect, but it is a high resistance. So the high resistance will certainly dominate here because we have only one hole, so to say. Then we come to the back volume. This is nearly a cube, a small cube, and we can give it a damping effect, yeah, a spring effect. So we say its inertia is negligible because it's quite a little displacement. Losses also not, because it's like cube, so it's a spring effect. And now we go to the intrinsic MEMS situation. So this is now special, but we have discussed already these losses in the perforations. I draw only one perforation resistor for the resistance through the hole. You could imagine each of the hole has a resistance, but I can simplify by doing an equivalent perforation resistor, which is which is related to 1 over the number of holes that we have. So it's in total, it is of course much smaller than a single perforation hole. Maybe we have 10,000 holes of very high resistance. So we divided the one resistance by 10,000. Then of course we have kind of a resistance which is lateral from the squeeze effect, which squeezes the air to the hole before it is exiting the holes, so to say. And then we have here a C diaphragm. So we have now a compliance for the spring of the membrane. So this is a mechanical compliance basically, or spring, which we have transferred into the acoustics domain. So the C diaphragm is basically mechanics divided by the area of the diaphragm. Then we can say we deal it as if it was an acoustical compliance. The expert sees immediately this cannot be an acoustic compliance because it's not against ground. It is between two other nodes, and for this it is already clear. And finally, we want now to get the pressure drop or the voltage drop in this circuitry at the diaphragm. So this would give us the displacement of our diaphragm finally. And by solving this network, we can do so. Now we have this structure somehow sketched into our situation. It helps a lot to understand how it's making up, but we can stretch it or redraw it in such a fashion so we can easier display this situation. So we see here the port, the radiation, the port, front element, the MEMS situation, the diaphragm pressure which we pick up here, ventilation bypass to the back volume. This is typically the situation. Yeah, and now simply we want to see what is these elements doing, how relevant are those acoustical impedances. You always take the situation that I compare with 1 kilohertz and maybe the 1 millimeter diameter diaphragm. And so I do for the radiation dimensions. So the radiation impedance in total, we get, if you put those numbers in, something like 4 times 10 to the 6 Pascal seconds per meters cube. And if you only do the ohmic loss or the radiation resistance, we see that it is 10 to the 4. So it is not the relevant in the total impedance. It is 2 orders of magnitude below the total impedance. So we see we have here rather an effect of the mass. Okay, we go to the port. Let's see what's the port resistance. Yes, the port is this hole in the package. It's like a tube plus aperture. We can add this together and we get an equivalent situation. We get something like 10 to the 6 Pascal seconds per meters cube. Again, we see it is not much different from the other impedance that we saw before, so it is for sure relevant. If we check then for the total impedances, for the mass in the port, of course, this is the volume here inside this port. We have had this before. We have an end correction for the hole inside, and we can have the port compliance, the font volume compliance, which is simply the font volume divided by density and C squared. And we get an impedance, a total impedance, which is in the same order of magnitude than the radiation impedance. So we see in this case, we take both of them, but they act differently. And yeah, just to see some constructions of port designs, I have here cross sections of different microphones. So this is this classical microphone for hearing aids with a spout. So this where you put in this tiny tube, and you have, of course, if you measure here already the volume and mass of this spout and the tiny front volume, this gives somehow a resonance to the diaphragm which is inside. And since this 4x4 millimeters is not too small, yeah, it's just a quite huge mask. This is if you compare this to the microphone that we are discussing right now, we see here the port mass is very low. The resistance is somehow higher, and the front volume is still large. So this is changing then a kind of a resonance of this situation. And the most advanced microphones, they invert the situation. They don't have a lid or a cap with a hole inside. They rather put the hole on the rear side of the microphone. So then the sound enters on the back side into this microphone, and then the package itself is the bigger volume. So then this is the back volume, and this tiny is the front volume. The tiny front volume, whenever you have something resonant, shifts the resonance to higher frequencies. So this is the three situations for port situations. Yeah, then we check for the back volume. The back volume compliance we can again simply calculate. And now we see this compliance is orders of magnitude higher compared to the port and the radiation resistances. So it's say 4 orders of magnitude higher. That means this is a real relevant impedance in my system. I really have to respect this, while those outside dimensions maybe it's not too critical. So back volume is the inverse what we see before. So if I have this big diaphragm, the back volume is large but not super large. And now in those two situations here, we have a small back volume. This is what we just saw. So this back volume is also limiting the performance of my microphone. And for this reason, people have reverted the construction with a small sound port on the bottom side and the back or the package volume equal to the back volume. So if the back volume is much larger, maybe 10 times larger, then my impedance is much lower, and I can use this lower impedance finally. Because we check now the compliance, the acoustic compliance of our diaphragm in comparison to the rest of the impedances. Yeah, as we know, we might have a membrane situation where we have stress and thickness of a membrane, or we use a plate situation where we have the bending stiffness. We can combine this situation. I have here an example with 30 megapascal and 300 nanometers. In this case, if you compare those both compliances, clearly the membrane one is dominating, is 6 orders of magnitude difference. So it's clearly a membrane and not a plate. And if I calculate the impedance from here, I have the diaphragm impedance 10 to the 6 times 10 to the 10 Pascal seconds. And now this compliance here and that compliance of the back volume is more or less the same. So this is like already impedance matching or sharing. So whenever we put in a pressure, 50% we find on this and 50% we find dropping on that condenser. So, or in other words, in such a situation where the impedance, acoustic impedance of diaphragm and back volume is equal, we lose 50% of the energy in the back volume and 50% we can use on the diaphragm to generate a signal. This is simply a fact, and this is, yeah, we discussed this in different aspects. Yeah, and question is now, this tiny hole, does it really harm situation. If we calculate this hole, and I have here 3 millimeter radius or diameter, I don't know, 1.5 micrometer and a 300 nanometer thin membrane. So basically it's a single white hole. We get 10 to the 13 Pascal seconds. So it's 4 orders of magnitude, 3 orders of magnitude higher than the impedance of those two acoustic elements. Yeah, and will this harm our system? We will see later when we do the modeling. Now it will not, for a certain reason. I have some examples for this ventilation situation. This is just a reference microphone in a wall where you measure the sound field, and of course it's equalized to the rear. If it is this case, or you have this frequency shape here, usually you measure the pressure in a sound field. That means the sound hitting the diaphragm, moving it, will also enter the ventilation hole. If the frequency is low enough, then we have cancelling of pressure inside and outside. This we see here below 1 Hertz. The lower we go, then the total pressure is changing inside and outside with the same speed. If you have higher frequencies, the ventilation hole cannot follow anymore, equalizing the inner. This is a typical situation. These are those capsules which are metal-based, and you screw a grid over the diaphragm, which is this one. And if you screw the grid on, you have a little tiny hole here inside the wall, which you can tune a little bit by screwing the system. So there's a delicate mechanical system of ventilating, because you need to have a very tiny and precise hole to generate wide bandwidth. If it is too big, and by drilling for far too big, you have issues to control those tiny holes. And we, in the MEMS situation, we have no issue in controlling precision of holes. So we can define such a hole by lithography with nanometer precision. We can multiply the number of holes by design. So we have a lot of means to control this ventilation, and with the ventilation we control the bandwidth, the corner frequency, and sometimes it's even important for speech recognition where you have this frequency. Just also to show, there was this floating membrane idea, which I liked so much because the diaphragm is then very sensitive, but the diaphragm which is floating has a circumference which is basically giving a channel for ventilation and is all around. So this is again not so easy control of ventilation. And it is a slit, not a hole, so the slit scales differently. It is for sure an issue in the design of such a kind of a microphone, yeah, because you don't want to have it close at the edge. Okay, so we are starting discussing pros and cons of designs already, yeah. So we have the diaphragm, the back volume. Now we check our perforation situations, and this is the equations from Spohr, which we simply calculate in here for the gap, so the squeezing and the perforation through the holes. And I have here this example of thickness of the backband, 1.5 micrometer. Radius of the holes is 3 micrometer, and is already 50% of perforation. So it's like a very open mesh. And I even give the number of holes that we generate here. So in this case, we have a gap loss of 2 times 10 to the 8, and the perforation nearly the same value. So even in this balance, losses by perforation and by gap fluidic losses is balanced. It's already quite wise decision. Yeah, the level is quite high, but we see here, since we divide by the number of holes, it is acceptable in some sense. Yeah, and here are some pictures of how people have done perforation. This this is just a broken device. We see here there's a backplate on the lower and the membrane on the top, which has cracks, of course, from preparation. You see here long holes, so the thick plate with holes inside. The gap, yeah, they could be more narrow, so it's a low perforation grade. It's a long tube. It's not a very good situation for perforation. And those guys have already much wider holes, but frankly spoken, this is something like 20 micrometer wide holes and 20 micrometer wide bridges in between. So the perforation, the gap resistance might be quite high because you have to float the air out, and then the perforation hole is of course wide, so the resistance is small. So I guess you need something balanced. This is the calculation which we discussed before, somehow balanced with 50% perforation. Nowadays, the backplates look more like this. It's like 70% of perforation, quite high wide holes, very little gap resistance. I would say the gap resistance in those systems, if we have only those tiny bridges, can be neglected. Yeah. So there's so many different ways of doing this perforation, but important in design. Yeah, this is for this last situation, simulation, fluidic CFD simulation. We have the diaphragm below, which is pressurizing the system. You see here the pressure from the diaphragm movement, the air gap, and we have the backplate thickness. You see here one hexagonal shape, just a unit cell with the hole inside. And we see how the gradient of flow through those holes is nearly no side movement necessary, but only this little loss in the perforation will dominate the whole system. Yeah. And now we have the whole system basically seen in terms of impedances. I put here aside, if you have our specific impedance of air divided by 1 millimeter squared, we get 4 times 10 to the 8 Pascal per second meter cube. So it is not so much different from the impedances that we see in our system. Yeah, and finally we see here the ventilation resistance, the highest in all. Then the perforation, most relevant for the damping of the system, much more than the port, for example, and the radiation. So this is how we can compare the system finally in terms of performance. And of course, since we have now an acoustic model, we also want to have an electrical model for this device. And I explain how we do this. So this is, well, again, the acoustical model, and we need to transform now into the electrical domain. And for this reason, we first again check for the electrical model of our microphone. So basically we say we have a variable capacitor, which is the parallel plate system, which is air-filled, and I could put an arrow in between to say this is a variable capacitor. Wherever the two electrodes overlap with each other, maybe with a dielectric to support it, you will have a parasitic capacitance from that. And of course, this is not adding up signal because it is fixed. And unfortunately, the dielectric has a higher specific dielectric constant. So it is a critical parameter because whatever signal I generate here will be divided down by this parasitics. And of course, also any amplifier that I have behind has also an input capacitance, even bond wires and stuff like this. The packaging will have parasitic capacitance. All is loading my active capacitance, and I have to respect. For simplicity, we to put the amplifier as a unit amplifier, and we can use this model to describe the electronics in a very simple way. And in between, we only have to do the transformer, as we discussed also in the second lecture. we can transform from the acoustics domain into the electrical domain by this ratio, which is basically the open loop sensitivity. This is the winding ratio of this transformer. Of course, we use an ideal transformer simply to transform these two domains. And then we are ready. We get from input pressure, output signal in volts, and we can start simulating our microphone. Yeah, some more words to the electrical capacitance. Yeah, of course, typically we have parallel plate situations, 100% overlap, we calculate 100% of this capacitance. Now we have a situation with holes. And a hole is, of course, a cutout in my plate, so it is reducing the capacitance. People have asked themselves, how much can I perforate my system and how much compromise can I do on the capacitance? But of course, if I lose electrical capacitance, I lose also sensitivity from there. So it must be somehow a compromise. And a very simple way of designing this system is that we say, okay, we have a small gap and we have holes in the order of magnitude of the gap height. Yeah, say if this is 2 micrometer and this is 4 micrometer, yeah, the stray fields that come from the holes are compensating partially the loss of the pure area. So in this simple formula, we have corrected by a smaller hole by radius of the height of our gap. So this is fair and is a simple idea. So if we have in this case 50% of perforation with those specific dimensions, we have effectively only 8% less capacitance than for the ideal plate-plate system. So this is for sure okay, and maybe you can do more of this. This is even FEM simulations of the stray field situation that is supporting the idea with the height correction. And this simple numerical compensation, analytical compensation compared with FEM simulation tells us that it holds quite well for a gap of 2 micrometer and perforation of 20 or 30%. It is more or less valid for up to some 10 micrometer. And you see here the ideal capacitance is 1, and maybe with 30% of perforation and even 7 or 14 micrometer hole diameter, we still have something like 80% of the total capacitance. So it is feasible to go for those kind of constructions and simply use those simple assumptions. Okay, just a simple check what is parasitic capacitances. Then we have our sensitivity. The gain is, of course, the division of the active capacitance by the total capacitance is, so to say, the gain of my electrical system times the amplifier gain. So you see here, it is dividing down by the parasitics. If you have a good microphone, maybe it has some 3 picofarads active capacitance, maybe some 1 picofarad of parasitics with some input capacitance. If we bias our system with 10 volts, for example, and we get a sensitivity of 17 millivolts per Pascal, a gain of 66%, that ends up with a sensitivity of 11 millivolts per Pascal. Still okay, so will never be ideal, but is somehow the situation that we face. We lose something with parasitics, and if you're good, we have intelligent designs with less parasitics. Yeah, now we check a little bit these transfer functions. What is going on if we have our model and scale something? You have some examples from simulation with measurements. This is simply the situation of this microphone before. We have different diaphragms, membranes, circular, spring supported, corrugated, and so on. It is getting more and more sensitive. We see here the sensitivity, low frequency is starting to increase, but what we see as well, the bandwidth is always lower. And of course, these are fabricated with the same perforation situation. And if I simply keep my damping as given and I increase my saturation, I reduce the bandwidth. So this unsensitive device had maybe some, say, 8 kilohertz of bandwidth. The very sensitive, which we wanted to have, has only some few hundreds of, or maybe 1 kilohertz of bandwidth. So if you have this situation, of course, you have to work next on perforation. Yeah, and this is a way to overcome perforation. And keep in mind, perforation goes, or the resistance goes with the radius to the force. We have here 2 steps improvement. That was the holes. If you look from the top side through the membrane, you see the holes. Low density, but a certain diameter. If you increase the density, you increase the bandwidth. We see here that is this situation here. 2 times the density is increasing a lot. But we did not change the diameter. And we had only a linear effect. But only by some 20% higher diameter, which is, of course, a technological effort to go through, we could get the full bandwidth then finally. So maybe 10 to 20 kilohertz. And this is, yeah, of course, understood by modeling, but to follow with technology is always quite some effort. Yeah, this is an example for different back volumes. Also, we have maybe a microphone with a certain sensitivity. Open is not really, or infinite back volume, I would say. Yeah. Then we put a back volume on the system, and the sensitivity a tiny little bit is reducing because the spring is in concurrent with the back volume spring. And then we get a smaller back volume, is this one, and a very small back volume, 3 millimeters, 0.3 millimeters cubes, is reducing the sensitivity extremely. But also what we see is that the bandwidth is always reduced on the lower end. So moving from here to there, I know is going with the ventilation. We have kept the ventilation constant. So the hole in the diaphragm is always the same. And of course, if the volume is finally very small, this hole together with the volume can be equalized very fast. And that means we get a corner frequency at higher frequencies. So the bandwidth of this microphone is not acceptable anymore. And we need to adopt then finally the size of this ventilation with respect to the back volume of your microphone. Yeah, this is something that you can even use in designs. I was in the beginning talking about this wind noise in the convertible. This is really a measurement in a Porsche convertible of those times, driving with 120 kilometers on the Autobahn. And this is the noise profile, wind noise in dB SPL. I don't know which is the reference. You see this is 40 dB plus for low frequencies, simply noise due to this wind effect. And of course, you can understand that the noise predominantly at low frequencies you would like to filter. And if you look at the microphone where we change the ventilation design, so the holes in the membrane which allow ventilation is in number 41836, so we make more of them, we increase the diameter of those holes, so we can eventually design a device which is with a corner frequency of say 100 Hertz. And if I look at 100 Hertz, then I have already 10 dB or this portion filtered, and let's say maybe I put it to 200 Hertz, then I am with 40 Hertz, which is this peak here, already 15 dB below the initial pop noise. So I can filter out quite effectively this popping and still be able to transfer voice. And in such a special application, this is for sure beneficial. Yeah, this is such kind of examples. Just I give you an insight how those systems are modeled in a professional way. This is in a cadence environment. The whole system described for circuit simulators on the ASIC side. We have here the pressure source from from outside. A customer port is even, so this might be your phone lid. Then we have the microphone total model, and here's the ASIC model to the outside. Yeah, and the ASIC model is of course detailed, starting with the customer port. You see here kind of a package specific circuitry. The microphone is exactly what we have discussed today. Finally, you find here the port and the diaphragm and the back volume, stuff like this, which we will discuss next time on a SPICE model maybe. We see here also kind of a transformer from the acoustical into the electrical domain. And then is the electrical capacitive situation of the microphone. And of course, I don't go into the ASIC model. ASIC model is much more complex, but we find a portion which is called the charge pump. This is generating the bias for the microphone. And we find a portion, this is the source follower, this is the input transistor to the microphone. So, and all together, this is being simulated in terms of signal bandwidths and finally also noise. And here's the inside of this microphone model, which we discussed before. And this is the result of such an element. We have in red real measurements of a typical device and the simulation of the frequency response of that respective model. It fits the corner frequency of the ventilation and package and so on quite well. It fits also the emerging resonance of the package situation. And of course, we are happy to predict this, and it's quite fair. Yeah, with this, I want to end this lecture. So once again, we reflect on the key performance parameters, signal noise ratio, acoustic overload point, and this under constraints of size, of course, also cost. Don't forget about this. Then I was giving you an insight into the Navier-Stokes and how to simplify this for our applications here. We have developed the lumped element model for the cross-section basically of the microphone, and gone into some details of diaphragm, perforation, and back volumes. And I've given you a little insight in scaling, how important those systems are. And last but not least, we will in the next lecture see how they depend on each other and how we can add on the noise simulation. So this is it for today. Thank you so much. I have to check. I stop sharing and then it's starting to save, I hope. No, I have to stop here.